So, sorry. Yes, well, so we made these simulations, we solved the Langevin equation, but this is the same as in all the other models, but we have to pay special attention to the motor dynamics now, because motors, like I said, they can diffuse along the cargo, and then now when they attach to the microtubule, we consider that they attach, but that when they attach, they link one node to the microtubule. So the force is actually, when they walk, the force is actually applied on one of the nodes and not all the cargo. So you have a balance of forces. The motor can walk a lot of steps here and then detach and diffuse again and then attach to the other node. So we have a balance of forces there that we believe are the responsible for this deformation of the cargo. In particular, we made experiments both first with teams of identical motors. This is one type of motor, being it kinesin or dynein, only one type, and different copies of these motors. And then we did the same, but with teams of opposed polarity. That means with both teams present and this tug of war scenario. So what you can see here is some of the observables we have from the simulations of identical motor teams. So what we have here is the position of the center of mass. You can see, as expected, that this, well, in light blue you have the cargo being dragged by 2 motors, and in dark blue by 10 motors. So you have a processive motion to all one direction, and as long as the motor number grows, it has more speed. It's all very expected. But what we also saw is that the length variation, you have fluctuations, you have elongations and retractions, but they all kind of prefer this contracted way. So you have fluctuations, but they all go around the negative ones. That means the cargo tends to contract. So if you were doing this in an experiment like CECI does, well, that's all you have, and you have no other information. But with the model, you can now access the motor distribution. So what's really important now is that we can access how are the motors distributed on the cargo as it moves. So we calculated this motor's relative position to the cargo. This is a dimensionless quantity. And we evaluated the probability density estimate. So here in purple, the purple dot line, you have 10 inactive motors. That's it. That means they don't attach to the microtubule, they only diffuse. So you have this really homogeneous curve distribution. And then when the motors can attach, remember that they only attach to one of the nodes, you have these peaks around the nodes of the cargo. And what's interesting is that as the motor number grows, the distribution becomes asymmetrical. So you have more active motors on the rear part of the cargo than on the leading edge. That means that, for example, with 2 motors of this size, you have a lot of extensions and retractions, and it's pretty symmetrical. So you have motors both on both ends, but with 10 motors, you have a predominance of the motors staying on the back. So this could explain why the cargo tends to contract. And so to quantify this, we evaluate this ratio that we call pull-push, being pull and push the maximum of this probability density. So pulling and pushing would be relative to the direction of motion. And what we find is that both for dynein and kinesin in different teams, they all tend to contract. They have all this ratio less than 1, and so this is like a rear wheel traction that cargo has when carried by one team only with various motors. And then with the tug of war scenario, where we have different teams with different motors going to opposite sides of the microtubule, but we observe now here is like a 10 versus 10 the curve. So we see that now in the position that you have reversions in the direction of motion, so we have this bidirectional transport I was talking about. Notice that this is a speed really, it's practically zero, like here, compared with another curve of 10 kinesins and 5 dyneins. You can see that it's really slow, but you have these there changes. And then when you see the changes in the length, you have also extensions and retractions, but now you have more elongations. So this is a change from the other experiments. And if you see at the motor distribution, what you see is here in blue we have the ones I showed you before of 10 kinesins alone, and then as you stand against them some team of other number of dyneins, you see that there's an inversion of the peaks. So this peak goes down and then the other one goes up. So in a tug of war scenario, you have a transition that goes from pushing to pulling the cargo. So there's an inversion in the distribution. So now you have elongations, and now you have different output. So we can compare this with experiments. We could reproduce the results from the experiments of FCEyN. So what we had is that extensions have less mean velocity than the other cargos. And so we can infer from this that mitochondria that retracts are probably carried by a single team of identical motors, and mitochondria that elongates are probably engaged in this tug of war between both kind of motors. So they have a low mean speed and they extend. So to sum up, what we have is we had some experimental data on mitochondrial transport, and we wanted to understand it a little bit deeper. So we extended this numerical motor and we came to this hypothesis. And so I think it's really good that it's a little step further to understanding the mitochondrial transport. So, well, thank you very much. If you have any questions?
Very well, very interesting. Other question?
Okay. Very, very nice work.
Thank you.
So, maybe I missed it, but in your Langevin equations that you solved, there has to be some decreasing potential or something that makes the motor move along the filament.
On the Langevin equation, actually, the motor only enters through the force it exerts on the cargo. So what we have is independent dynamics for the motors that is here. So you have the force, and the force depends on the position of the motor. The position of the motor, I would say, is independent from the Langevin equation. So because you have these complicated dynamics where the motor can diffuse or they can attach, and when they attach, they always they have a probability to take a step, and they always step in the same direction. So this is all a stochastic
okay, so
cycle.
you build in the fact that they can only move in one direction.
Yes. There are some works that consider the possibility of backstepping, but that's very low probability. They have very low probability of backstepping. So yes, this is like evaluated in a Monte Carlo procedure. You have different rates for attachment and detachment, and the probability to take a step, and detachment and stepping all depends on the force the motor is exerting on the node. So
very nice, but perhaps it's a very nice question, but the symmetry in the peaks is because you are focusing on the number of motors, but they have maybe different biophysical properties. So if you normalize the number by, I don't know, the binding rates or the detaching frequency of the channel, do you think that those peaks would be equal?
I'm sorry if I wasn't clear enough. This is the distribution of kinesin. That is the one that I showed you here. So what we are seeing is only the distribution of kinesin now. It's if you look at the dynein distribution, you will see something more or less the same, but reversed because kinesins move to the other side. So I don't know if that was your question. So this is only kinesin. Kinesins go to the other side.
So you said that the pullers, these walking machines,
Yes.
they need ATP.
Yes.
So you are not modeling. So my first question is: every step consumes one ATP, or is it because it really? Because then it would be really important to understand how the ATP gets to the machine on time, so that it can move like rhythm.
Yes, there's a lot of works mainly dealing with that, and what I can say that kinesin, I think they do consume 1 ATP per step, but dyneins don't. They have a lot of binding sites, like 6 binding sites, and it's not really clear how ATP is consumed. There's still a lot of debate, and there are models that instead of doing these transition rates, they mainly deal with chemical reactions with ATP, but it's equivalent. So there are experiments with less concentration of ATP and more concentration. There are works done.
Any other? No, I have just another question. So since you have concrete trajectories, can you fit somehow parameters in order to reproduce what you observe experimentally and plug into the model and see whether you? So you have concrete trajectories on on microtubules. Okay?
Yes, the experimental ones.
The experimental ones. So could you? Because I imagine now we have put. A dimensional parameter, velocity, average velocity 1, I don't know, something like this, but something that allows you to fit the kind of trajectory you observe on a real microtubules with your model?
Well, I don't know if I get you right. So you have these kind of trajectories in experiments, and we have equivalent ones. We are not interested in fitting exactly, because these are all stochastic trajectories.
Not exactly the trajectory, but mean characteristic. I don't know, the average. I don't know, some statistical observable that you could pinpoint to the model that would allow you to. Yes. So how many parameters is your model?
Well, there's a lot of parameters. There are some that are exactly the same. I have them around here. So you have all these parameters. These are all, most of them are measured in vitro experiments for the motors.
Okay.
And then the parameters that we added are the stiffness of the cargo and the viscosity. Those parameters we kind of we checked that we have things.
More or less.
Yes.
Something.
Yes. So we did some evaluations with different cargo stiffness. So we start with the ones that gave us observables similar to those in observed in experiments. For example, 20% of elongation change.
Okay.
But there's not much in literature for mitochondria, for example, but those in the motors, yes, they are all tabulated and things measured. No, if that answers your question?
Yeah, perfectly answered my question. Okay.